P30 impression as well. All right, ladies and gentlemen, I do hope that you are having a great time with us so far, listening, of course, to just some inspiring ideas. We're going to move on to introduce our next opening keynote, and you might have already, of course, glanced over there to see who our speaker is. I also want to remind you that we are using Pigeonhole for you to, of course, send in your questions for our speakers. We will do our very, very best to answer as many as we can. We would like to do a quick photo of this right now. It will be useful throughout the entire day, today and tomorrow as well. The code is beyond to enter the, of course, chat. Now, ladies and gentlemen, up next, very exciting, our keynote presentation, Accelerating Physical AI with Open Source Robotics. And ladies and gentlemen, we're all ready to bring on our speaker right now. This session is co-organized by A-Star, ARTC, brought to you, our good friends over there at Ross I Consortium Asia Pacific, supported by EDB, NRP, and SGI. I'd like to welcome staff software engineer from Intrinsic for the opening keynote. Please welcome Mr. Yadanu Vijay. A warm welcome.
Thank you. All right. Good morning, Singapore. Thank you. All right. I'm super excited to be here on stage at Switch, at the Beyond stage especially, to talk about my favorite two topics, robots and open source software. And I'm sure it's your favorite topics as well. In particular, I'm excited to talk about how we can accelerate physical AI with open source robotics. We'll start by looking at what these open source software stacks are. What is physical AI? What is this new trend that we're seeing today? What are some new challenges and requirements it's posing for the robotics community? And how we plan to tackle some of these challenges. So let's jump right in. My name is Yadu Nand. I go by Yadu for short. I'm a staff software engineer at Intrinsic. And those of you who don't know, Intrinsic is part of the Alphabet ecosystem, so similar to Waymo. But our mission is to democratize the access of robotics to one and all. I've had the privilege to work on several open source stacks, including ROS and OpenRMF for a few years, and I'm on the project management committee and a core maintainer of the same. If you're not sure what these softwares are, we'll get into them in a moment. But today I'm on stage on behalf of the Open Source Robotics Foundation, or Open Robotics in short, and OSRF is a nonprofit with the mission to support the development, distribution, and adoption of open source software. And in particular, to support researchers, developers, R&D professionals to create products, education tools, and high-quality robots for everyone. There are several projects that are under the stewardship of OSRF. We'll start by looking at ROS. How many people here know what ROS is? Not enough people. All right. So ROS, or Robot Operating System, is really just an SDK at the heart of it. Think of writing a software for robots. A robot has to do a lot of different things. It has to process a lot of data. It runs several algorithms to process this data and handle this data and then take action on the physical world. Writing all of this in a single program can become really complicated. Anytime you want to make a change, that's going to be hard to do. How do you test it? How do you deploy it? So what ROS does, it gives you the ability to split up this giant program into a collection of smaller programs that we call ROS nodes. And each node typically does one very small function. And how do these different nodes synchronize or get data to one another? This is what ROS helps with. So there's a plumbing aspect to ROS, and it helps by defining standard messages. Here's what a camera message looks like. If you have a LiDAR on your robot, this is what the data is represented as. So ROS defines a lot of these standard messages, and then it provides the plumbing for these nodes to be able to communicate with one another. Building upon this bedrock, the community has added a whole bunch of capabilities to ROS. With all of these capabilities, you can do state-of-the-art motion planning, control, perception, etc., and really go from a collection of hardware to a fully functioning robot in a matter of just weeks. So ROS is distributed by OSRF, and every year we have a new release. So some of these logos you see on screen are some of the releases we've had recently. Our latest one is called Kilted Kaiju, and this is the 11th release of ROS 2. When developing applications with robots, it's often really challenging to test with physical hardware. It's going to be expensive, it's a slow process, and it's really hard to scale. So what we need in robotics is a really good physics-based simulator that can emulate the physical world. And this is needed as oftentimes we're developing in simulation. We're able to iterate much faster. We can step through simulation much faster than the time in the real world. And to support simulation efforts, the foundation has Gazebo. This is our flagship physics-based simulator. We just had our 10th release of Gazebo, Gazebo Jetty, and it's feature-packed to support the AI and reinforcement learning community. Another project that Meng Fai also touched upon is OpenRMF. Now, this was a flagship project of the Singapore office at Open Robotics. When ROS solves the interoperability problem within a single robot, there needs to be a solution for interoperability among robots. And this is the gap that OpenRMF fills. So oftentimes in facilities, you'll have robots from different brands that need to coexist. And historically, one way to overcome this, or overcome the challenges of dealing with multiple robots in the same space, is to separate them. We have robot A operating in this environment or this space, and robot B somewhere else. What OpenRMF does is bring in this understanding of different heterogeneous fleets. And what it really means is now different robots from different brands all talk the same language. And once you talk the same language and understand one another, you can build intelligence on top of this. So OpenRMF has a lot of intelligence related to traffic planning, task planning, interacting with building systems like doors, elevators, etc., to really supercharge your robotic deployments. We're not just a foundation that manages software. We also have our flagship hardware product called the TurtleBot. And this has now become the standard for learning ROS, and it's a great entry point for robotics, for young professionals, from students, all the way up to seasoned veterans. There are nearly 20,000 TurtleBots that we've sold. And this is a product that we not only co-design and license at Open Robotics, but it's something that we make available through several partnerships. So we have TurtleBot 3 that's distributed by Robotics, and TurtleBot 4 that's manufactured and sold by ClearPath Robotics. All right. So recently, we've had this initiative in the foundation called the Open Source Robotics Alliance. And this is an initiative from OSRF to really organize and strengthen project governance and community involvement. It uses a mixed membership model. So the membership includes companies that are actively contributing to ROS, but we also have a meritocratic system where if you're someone who will benefit from ROS, you have the opportunity to join us and support our efforts here. We'll talk a little bit more about how you can join OSRA towards the end. But I'd like to jump into the heart of today's topic. Could anyone tell me what all these robots on the screen have in common? All right, this is a great audience, makes my job really easy. Yes, all of these robots here are powered by ROS, and they all have simulations setups in Gazebo. And some of them are even controlled by OpenRMF. So we've been building robots for many years, and we're using open source tools to really accelerate this development. But what really is a robot? At the heart of it, a robot is a system that does three things. It perceives or senses the world around it. It then processes all of this information to come to some logical conclusions. And then it takes action on the physical world. And historically, we've had software stacks for each of these layers. So we have things called drivers that talk to physical hardware, like a camera or a motor, to exchange data with it. And then to do the thinking, we have software stacks related to perception or planning that ingest the information from these sensors, plan something, and then pass it on to a control stack to effect change in the world. But historically, a lot of these robots are programmed using a model-based approach. This means that we need to mathematically model the physical world, we need to model the robot, and then come up with some equations or relationships between the two. What we're seeing recently is a shift in paradigm on how these robots are being programmed. We're moving away from this model-centric approach to a more data-centric one. And all of this is possible thanks to advancements in AI, together with lowering of costs in computation, and through accessibility of data as well. We're taking a page from the LLM community. in gathering large data sets and being able to train general purpose models to do tasks. So what's different now is instead of having these algorithms that rely on equations and models to figure out what the robot should do next, we're relying on neural networks or AI policies to figure out what the next output of the robot should be. And this is really enabling robots to operate in more dynamic environments and handle more complicated tasks. But how are these policies trained? Well, we need a lot of data. And data can come from many sources. There's no replacement for the physical world, so getting data from real hardware systems is the best option we have. But this can be a slow and laborious process, so oftentimes we rely on simulation to get the data that we need. And once we have all of this data, we can then train these policies. There are several state-of-the-art techniques, and there's a new policy or a new technology coming out every single week. But in general, they're either based on reinforcement learning, behavior cloning, or imitation learning, or some kind of hybrid approach. The goal of the training is to produce some kind of policy. This could be a neural net or some kind of binary that produces the outputs that the robot needs. But the million-dollar question is how much data is needed, and the answer is always yes. Right? So it seems like we need internet-scale data to be able to do some of this stuff, especially if we want to build robots that can handle general-purpose tasks. There's a really famous data set that came out through many researchers, both at Google DeepMind and all around the world, called the Open Embodiment Data Set. And this has over 1 million or 2 million data sets from various different robots. And we're talking about robot arms, mobile manipulators. They have different morphologies and shapes, and they do different types of tasks. And the goal is to collect a lot of data and to be able to train a general purpose model. So while we might be changing the way we program robots to do tasks, the way we interact with robots has not changed. We still need to be able to describe robots in some standard format. I need to know that this robot has 6 degrees of freedom. This is a robot arm. This is a mobile robot, etc. I also need to know how to get data in and out of the robot. Here's how I subscribe to the camera topic. Here's how I ask the robot to move. So the way we communicate with robots hasn't changed. We need to do this in the same way, whether we're talking to robots in sim or in the physical world, right? And when we're training, we need to collect data in a certain way, but we want to make sure that when we run inference with these policies, we're using the same data pipelines. And if we look at ROS, this is really the bread and butter of ROS. So historically, the problem that ROS has solved is ensuring that we're all talking the same language in robotics. So we're able to piggyback on ROS for this need to talk to physical systems, right? The ROS ecosystem already has a lot of useful message definitions to talk to different robots and sensors. There are already established standards to describe the morphology or embodiment of robots. There are plenty of drivers in the ecosystem to talk to these systems, so you don't have to implement a lot of software yourself. There's a lot of controllers for good real-time performance, and many, many tools for collecting data, visualizing them, annotating them, etc. And today, it's possible to take ROS as it is and build applications for physical AI. So you can use ROS and ROS drivers to collect data from the physical world, be able to use other open source frameworks like LeRobot, which has state-of-the-art algorithms for reinforcement learning, and be able to command not only a robot in the physical world, but also something in the simulation world. So if all of this is possible, what are some challenges? Well, although this is possible, oftentimes the integration is bespoke and non-trivial. Right? When we look at the community working on these problems, it's individuals from the machine learning or AI space who are not necessarily familiar with tools in the ROS ecosystem or the ways we develop and maintain software. So there's a gap today in how you access ROS and tooling today versus how people working in the space want to be able to work with it, right? And on top of that, there are also some needs. We need more standards. Maybe an embodiment like a tactile gripper is not well supported in ROS, or a new type of robot, a hexapod, or one of those spider robots. Maybe we don't have good ways to describe these systems and further communicate with them. So more standardization is needed. And while we can collect data from robots over ROS, all of this data often gets stored into a format that we call ROSBag. It's just time series data. But oftentimes, to train these models, we need data in a tabular format. So there is a gap right now in converting data that we store, that we collect over ROS, and having it available in tabular formats to train AI models. There's also a big challenge with installing it and managing dependencies. ROS really aims for stability. We're looking for deploying a robot that'll run in the field for 10 years. So we're very, very careful about providing packages that will become dependencies for the software that you build. But a lot of researchers in the ML community are relying on the state-of-the-art packages, and there are new versions of these packages coming out on a nightly basis. So we need to rethink how we can support some of these packages when building ROS-based applications. And finally, we're also missing good reference applications. While all of this can be done, it's easy to talk about it, there's no good starting point for the community to start building off of. So they say if you want to go far or go fast, go alone. But if you want to go far, go together. And at the foundation, we've kicked off this initiative that we're calling the OSRA TGC Special Interest Group for Physical AI. That's a mouthful, but we're just shortening this to SIGPI. But this is really a group of members who are at the forefront of this field, right? So these are distinguished individuals working in the cutting edge or bleeding edge of robot learning who have come together to say that ROS is going to be the backbone for physical AI. We're seeing the value in this. There are some gaps today, but let's all come together and work on this problem together. So you'll see a whole list of companies up here from Robotics, Huawei, Locus Robotics, Ross Industrial Asia Pacific, NVIDIA, Rerun, Intrinsic, the Ray Institute, AMD, Red Hat, BMW, Ecumen, Google DeepMind, PAL Robotics, Meta AI, Orb, Constructor University, Bosch, Dextery. So this is the who's who and whoever's working on state-of-the-art robot learning. So it's really amazing that we've been able to get these people together and commit to working on making ROS the backbone for physical AI. So what is our vision? We've recognized that there are some gaps today in the tooling that we provide at OSRF. So we want to consolidate and standardize further how users in the physical AI space can interact with robots. We want to build upon the existing abstractions and increase them where needed. We also want to make it easier for developers and researchers, particularly those in the Gen I community, to get started with building on top of ROS. And the way we're going about this is through working groups. So we've organized ourselves into 4 working groups to tackle these problems in parallel. First, we have the working group working on standardizing interfaces and messages. So there are some good standardizations in ROS today, but we need to expand on these. So this is what the focus of this group is going to be. But there are also some gaps. We need to be able to natively support data formats like tensors, or these formats are the formats that are used to store and propagate models. We need a way to be able to transport data a lot more efficiently. And we need some canonical design setups to show the community how to use these standard messages, right? We're also lacking some tools to better introspect, label, annotate, and visualize the data. And we need to create some standard tooling to go from ROS bags to tabular formats that ML researchers can use for training. And that's going to be the focus of the data visualization group. Finally, we have the training and execution groups and the reference platform and application groups. The training group's going to work on making it really easy to bring your own policy and plug it into a ROS-based application and have it function as expected. We're also going to work on adding new controllers that will be needed to interact with the physical world. We're going to look at how we can make ROS a lot more efficient for running systems on real-time compute, as well as synchronizing clocks across different systems, which is going to be critical. The reference platform and applications group is really going to be the bottom of the funnel of all the other working groups. We're going to commit to putting out high-quality reference applications out there for the community to build off of. And just like we have the TotalBot today, we're looking at other reference platforms that can help researchers and developers get started in the physical AI space. We're also championing what we call simulator interoperability. And this has also been a really nice initiative at the foundation level. So we recognize that there are several open source tools out there, and we don't want to restrict anyone from working with certain tools. Simulation, as I mentioned, is really critical in this space. The only hope of getting in the data that we need to solve these problems is from simulation. So we want to be able to tell researchers that you can use whatever simulation you want and just rely on ROS, and we'll be able to get data in the same way and we'll be able to control your robots just as you would expect. So recently, there's been this push among companies or foundations like the Open3D engine, Gazebo, which is under the OSRF Foundation, as well as Isaac Sim and NVIDIA, to standardize on interfaces to talk to simulators. So now, using the same code, you can send requests that all these different simulators will then honor. And this is going to make it really easy to collect data from different simulators. And why is this important? In order to solve this generalization problem, we need to be able to randomize at a scale that we haven't seen before. Randomizing in the physical world is often challenging, but we can often piggyback on simulators to quickly randomize and generate more data sets. So how can all of you help? Well, I'd love for you to take out your phone and scan these QR codes. Right? The first QR code will send you to our project landing page. It has some instructions on how you can contribute. Every contribution is significant, whether it's a fix to our documentation or a new feature that you add. But also, please join the OSRA. Join us, help us consolidate the ecosystem and really strengthen our mission to democratize the access of robots to one and all. That's my time. Thank you very much.
Ladies and gentlemen, let's hear for Yadu for an excellent keynote. And of course, he's here to connect with you as well. It was so nice hearing from you. Once again, we send him down with a very big round of applause. You can hear it. You did such a great job, Yadu. Thanks for covering so much. Ladies and gentlemen, up next, more exciting content coming away from Ross, because we know we love Ross. So next, you will be getting an exclusive look into how Ross Industrial is shaping the next wave of robotics adoption worldwide. We're delighted to bring to you our consortium